Dear friends, today we are going to discuss the mineralogical characteristics of basic, igneous and ultramafic rocks. In this we will discuss introduction, basic igneous rocks, ultramafic rocks, origin of ultramafic rocks and the conclusion. Rocks are essentially the constituents of the Earth's crust. The crust of the Earth, however, is said to have been formed first due to the solidification of the uppermost layer of the molten planet. It may be stated therefore that the first formed crust of the Earth was obviously the product of the consolidation of the molten silicates, that is, magma, and these may accordingly be described as the igneous rocks. Such rocks are also known as the primary rocks, since these were the first formed rocks on the surface of Earth. Thus, igneous rocks are the products of the consolidation of magmas, that is, the molten silicates which underlie the solid crust of the Earth. Igneous rocks are the most important of the three types named from the Latin word igneous, meaning fire. They are formed by the solidification of molten matter called as magma on cooling. Magma is formed at unknown depths in the Earth's crust and uppermost mantle. It may flow out on the surface from volcanoes as lava or may solidify below the surface. Rocks formed on the surface from lava are called as volcanic rocks. Those which are formed by the crystallization of the magma below the Earth's surface at greater depths are called as plutonic rocks, while those at intermediate depths are called as the hyperbasal rocks. Igneous rocks contain the following common rock forming minerals such as plagioclase feldspar, olivine, potassium feldspar, pyroxene, quartz, amphibole, biotite and muscovite. The percentage of these minerals present in the igneous rocks determines whether it is felsic, intermediate, mafic or ultramafic. Felsic rocks are those that are light in color and are mostly made up of the feldspars and silicates. Mafic rocks are darker colored and are mostly made up of magnesium and iron. Intermediate rocks fall somewhere in between, being felsic and mafic. Ultramafic rocks are very dark colored. Basic igneous rocks represent more slowly cooled intrusive bodies of mafic magma that never reach the surface. Basic igneous rocks or gabbroic rocks are produced in much the same tectonic settings as basalts. Mafic rocks are compositional equivalents of the basalts but have phanerotic grain size. Mafic rocks in general are essentially derived from the same type of magma crystallized under different conditions. Basic igneous rocks exhibit the following textures. They are hypidiomorphic or gabbroic or equigranular, reaction texture, that is caliphytic rims or coronas, exolution texture, ophitic texture, intercertal and intergranular texture and orbicular textures also. Mafic igneous rocks show mesocratic color index. Basic igneous rocks are classified on the basis of the content of the plagioclase, pyroxene and olivine. Accordingly, basic igneous rocks are classified as number 1 anorthosite, number 2 norite, number 3 olivine gabbro or ossipite and number 4 troctolite. Anorthosites are essentially made up of 90% basic plagioclase, that is labradorite, plus 10% or less ferromagnesian minerals. Norite is a gabbro in which the predominant pyroxene is hypersthene or instatite plus plagioclase feldspar. Olivine gabbro consists of the basic plagioclase, clinopyroxene and olivine. Troctolite is made up of olivine, plagioclase, that is labradorite, and pyroxene. Accessory minerals mainly includes apatite, titaniferous magnetite, ilmenite, pyrite and pyrrhotite. Gabbro can be formed as a massive uniform intrusion via in situ crystallization of pyroxene and plagioclase, or as a part of a layered intrusion as a cumulate formed by setting of pyroxene and plagioclase. Gabbro is an essential part of the oceanic crust and can be found in many ophiolite complexes. Long belts of gabbroic intrusions are typically formed at proto-rift zones and around ancient rift zone margins, intruding into the rift flanks. Alkali gabbros exhibit coarse to fine gabbroic texture. The different types of alkali gabbros include orthoclase gabbro, that is cyanogabbro, isexite, theralite and sekinite. Orthoclase gabbros consist of plagioclase, clinopyroxene and more than 5% of orthoclase. Isexite contains equal amounts of plagioclase feldspar, titanogite, amphibole and biotite, usually with some nepheline. If olivine is present, it should be called as olivine isexite. Potash feldspar is usually present. Theralite includes minerals like labradorite, augite, nepheline with or without sodalite, olivine, a little biotite and sometimes the hornblende. Sekinite is made up of labradorite, augite, amphibole and analcite. Accessory minerals in alkali gabbros includes apatite, sphene, magnetite and ilmenite. Alkali gabbros are a rare group of rocks occurs in a complex hyperbasal associations such as differentiated silts or volcanic complexes. Alkali gabbros are the products of assimilation and reaction with country rocks, mingling of alkaline, that is cyanitic or even granitic magmas with basic or ultra basic material also produces alkali gabbros. They are also the products of normal differentiation products, anorthosites formed by crystal sorting, perhaps with the assistance of filter pressing, due to the squeezing of the magmatic chamber by tectonic forces. Banded anorthosites are a result of fractionation during the crystallization. Dolerites are basic igneous rocks formed under hyperbasal conditions. Mineralogically, dolerites are made up of plagioclase and pyroxenes. Sometimes olivine may also be present. They show typical ophitic or subophitic texture and their color index is mesocratic. They occur mainly as dikes intruding into the country rocks. Basalts are basic igneous rocks formed under volcanic conditions and hence are extrusive in nature. Basalts are mesocratic. They consist of plagioclase, clinopyroxene and sometimes olivine. They exhibit basaltic or intersertal intergranular textures. They are found both in the continental crust and oceanic crust. Basalts are tholeitic or alkaline in composition. In tholeitic basalts, pyroxene, augite and orthopyroxene or pigeonite and calcium-rich plagioclase are common phenocryst minerals. Olivine may also be a phenocryst and when present may have rims of pigeonite. The ground mass contains interstitial quartz or tridymite or cristobelite. Olivine tholeite has augite and orthopyroxene or pigeonite with abundant olivine, but olivine may have rims of pyroxene and is unlikely to be present in the ground mass. Alkali basalts typically have mineral assemblages that lack orthopyroxene but contain olivine. Ultramafic rocks represent the most slowly cooled intrusive bodies of mafic magma that never reach the surface. Ultramafic rocks in general are crystal differentiates of the basic magmas. or basaltic magmas. The plutonic ultramafic rocks are classified according to their content of the mafic minerals, which consists of olivine, orthopyroxene, clinopyroxene, hornblende, sometimes biotite, and usually small amounts of garnets and spinel. Textures of ultramafic rocks. Ultramafic rocks show variable textures in dunite and other peridotites. The olivine is almost invariably anhedral and in oval to rounded grains. The unaltered varieties may be strongly granulated. A small amount of pyroxene in the peridotite is almost always interstitial to the olivine. The pyroxene forms large poikilotic plates enclosing several olivine grains. These large plates reflect the light in the outcrop, giving it luster, mottled appearance, or a rare texture of pseudoporphyritic texture in which large subhedral crystals of enstatite are enclosed in a granular matrix of olivine. It is possible that these are phenoclast or phenocryst rather than phenocrysts. In peridotites in which the pyroxenes are more abundant, the pyroxenes at a time form overgrowths on olivine grains and then are usually anhedral, although the grain boundaries are often straight where they meet one another. In other peridotites, they appear as large anhedral plates, the smaller olivine occurring here and there at grain boundaries, although rounded rather than interstitial. Hornblende and biotite in small amounts form subhedral crystals with prismatic and platyforms, respectively. In hornblende peridotites, in which the hornblende is a major constituent, usually forms poikilotic plates. Outcrops of this type of rocks have a striking splendid appearance due to the reflection from the broad cleavage places of the amphiboles. In hornblendite, which consists predominantly of hornblende, the latter is usually coarse, stumpy crystals, usually with interstitial quartz and feldspar, interwoven elongated crystals, and more typical of the metamorphic rocks. As usual, texture in pyroxenites, which in the magnetite and ilmenite is known as cedronitic texture, is also found. The pyroxene and other silicates are subhedral to euhedral crystals enclosed in a matrix of magnetite. Plagioclase in peridotites and troctolites is cut by numerous cracks, apparently due to the expansion of olivine during serpentinization. Varieties of ultramafic rocks in which the dunite is virtually pure olivine rock with a small amount of enstatite, chromite, magnetite, etc. The names of the minerals may be prefixed. For example, enstatite, dunite, Herzbergite is composed of olivine and orthorhombic pyroxene. Saxonite is a synonym. Johansen uses Herzbergite for olivine enstatite rock richer in iron ores than saxonite. Verlite contains olivine or diallage. Lherzolite contains olivine, diallage, and orthorhombic pyroxenes also. Skylite is a mica hornblende peridotite. Cortlandite is a hornblende peridotite. Shishimite is a hornblende peridotite with diopside and phlogopite. Montrealite is composed of clinopyroxene, hornblendes, and olivine. Picrite contains olivine, titaniferous augite, and barkevicite or hornblende. Some labradorite and analcite are usually but not always present. Diallagite is composed predominantly of diallage. Hypersthenite is composed largely of hypersthenes. Bronzitite is made up chiefly of the bronzite. Enstatolite is predominantly enstatite. Websterite is composed of hyposthenes and diallage. Saguendite consists of carbonate with magnesite and enstatite. Kimberlite is an ultramafic rock occurring in dikes and pipes like intrusions, which normally swamps with inclusions of all rock, and in part it may be tufaceous. The principal mineral is olivine, usually altered to serpentine. Bronzite, chrome diopside, phlogopite, perovskite, pyrope, ilmenite, chromite, apatite, magnetite, and many other minerals are found. These minerals occur in a ground mass of serpentine and calcite. Millelite has been reported from American kimberlites and has been suspected in others also. On the basis of this mineral, some authors regard kimberlites as an altered millelite basalt. Occurrence of ultramafic rocks. Ultramafic rocks occur in a variety of ways. They are found as emplaced bodies or enclaves within the country rock. They form layers in the lower part of the differentiated cells and complexes. They are found as inclusions and basaltic flows. Sills, dikes, stalks, and irregular bodies of ultramafic rocks are widely distributed. Serpentine intrusions are characteristically distributed along the orogenic zones, including geosynclinal sediments. Funnel-shaped intrusions also are of wide distribution. Economic minerals associated with the ultramafic rocks. The principal valuable minerals produced from the ultramafic rocks are related rocks are asbestos, chromite, magnesite, nickel, vermiculite, platinum, and diamond. The asbestos occurs as fibers in veins cutting off the peridotite mass. The veins are never extended beyond the boundaries of ultramafic rocks. They are often double, the two sets of fibers being separated by a parting made up of strings of magnetite crystals, sometimes with flanks of serpentinite wall rock. The scarcity of commercial asbestos deposits compared with the abundance of the serpentine bodies throughout the world is the most puzzling feature of the origin of the asbestos. Chromite deposits are of two types. They are disseminated crystals of chromite, apparently of early crystallization, expectable from positions of spinel in the reaction series. In addition, pockets and veins of chromite appear to cut the ultrabasic rocks at least locally, and therefore must be relatively late crystallization over a partly or fairly protracted period from the beginning of the crystallization to the stage of serpentinization. Small deposits of nickel are found in serpentine and peridotite bodies associated with differentiated cells and isolated small intrusions. The sulfides carrying the nickel are always disseminated grains or pods that replace the serpentine. They are usually limited to intrusive and the nickel in them that might have been derived from the olivine during alteration to serpentine. Among the chief sources of platinum metals are peridotites and ultrabasic phases of the banded complexes. Nickel also is obtained from the soils produced by the tropical weathering of the peridotites that contain small amounts of nickel. Huge tonnage of this material are found in the Caribbean, Northern and Southern America, and New Caledonia. Magnesite occurs as a replacement of serpentines. Magnesites formed in this way are very dense and fine-grained due to the fine-grained rocks replaced. Macroscopic vermiculite deposits are found associated with the ultramafic rocks like dunite or pyroxenite when they are intruded by the acidic intrusion. Meteorites and ultramafic rocks in the composition are similar to ultramafic rocks. Siderite types of meteorites are made up predominantly of the nickeliferous metallic iron, and aerolites are chiefly made up of silicates such as olivine and orthopyroxene, and less commonly as plagioclases. The siderites are of considerable interest because of the possibility that they are material like that of our own Earth's core. Etching brings out interesting textures, the iron meteorites, and are classified according to these textures. Some iron are spongy, containing inclusions of olivine and pyroxene. The aerolites are most interesting to study in thin section because of their similarity to composition to the terrestrial rocks. Commonest stony meteorite is chondrites, which are characterized by roughly spherical bodies called as chondrules, made up of skeleton crystals in glass radiating fibers, glass or nickel iron also. Crystallized silicates in the chondrites are olivine or pyroxene, and they are embedded in a fractured or brecciated base of the olivine or pyroxene, often cut by veins of glass or ultramalonite. Rarely, meteorites have a basaltic or gabbroic texture. granular or brecciated textures are also found. Thus, ultramafic rocks show similarities with the meteorites. The peridotites and pyroxenites present a problem in petrogenesis because many are essentially monomineralic rocks and as such may be expected to have melting temperatures much higher than usually regarded as likely for the igneous rocks. This does not introduce a problem in the origin of the bands of peridotite and pyroxenite in the banded complexes because here they evidently result from crystal accumulation during the crystallization of the basic rather than ultramafic magma. Nor it is a concern in kimberlites and similar rocks that are not monomineralic. Many occurrences of pyroxenite and peridotites are not, however, parts of the banded complexes but are independent bodies, dikes, sheets, stalks, etc. Solid crystalline masses that have moved in dynamic processes. This is supported by frequent granular appearance of the olivine and evidence of granulation, sometimes observed in the fresh dunites. Hess, on the other hand, has argued that peridotite magma has been intruded, the liquid condition being the result of the high water content. This seems theoretically unlikely. It has also been suggested that mechanical intrusion of peridotite may be facilitated by the lubrication of calcite masses by colloidal, hydrous magnesium silicate or serpentinite. However, serpentinite displays much evidence of this deformation. Still, another possibility is that the olivine was brought in suspended in basic magma and that subsequently the magma was largely squeezed or otherwise separated from the olivine or olivine and pyroxene. Luckily, this suggestion is supported by the occurrence of basaltic borders on peridotite masses. It is also possible that subsequent serpentinization and alteration may destroy fine-grained or glassy basaltic material that originally formed the matrix of peridotite, although a satisfactory situation or solution is not yet available for all types of peridotite intrusives. It seems unnecessary to assume a peridotite magma. The cause of serpentinization is another problem of considerable interest in these rocks. The most significant feature is perfect pseudomorphism, frequently without any evidence of the deformation due to volume changes. Other relevant features are absence of serpentine, development in the wall rocks, and variation in the degree of serpentinization depending on the wall rocks. Thus, peridotites in granites and crystalline gneisses usually are not as thoroughly serpentinized as those in schists, slates, and other water-rich rocks. Thus, it is possible, if not predictable, that much of the water responsible for serpentinization can result from deuteric solutions provided by peridotite alone, as serpentine consists or contains about 15% water, and any magma from which the peridotite may have crystallized would not contain water in such quantities. Such possibility of hydrothermal source for serpentinizing solutions cannot be disregarded, but in many instances there is still evidences to support it. The experimental work of Tuttle and Bowen suggests that the development of talc rather than serpentine is a function of temperature in presence of a high water pressure. Thus, talc is stable above 500 degrees Celsius, whereas serpentine is the alteration product to be expected below this temperature. If carbon dioxide is abundant in altering solutions, magnesium carbonate also becomes an important secondary mineral. The experimental investigation mentioned also suggests the possibility that olivine may replace pyroxene in the presence of abundant water vapor. Basic igneous rocks or ultramafic rocks represent more slowly cool intrusive bodies of mafic magma that never reach the surface. Ultramafic rocks in general are crystal different shades of basaltic magmas. These rocks are economically very important as they host some of the mineral deposits like chromite, platinum, diamond, asbestos, talc and vermiculites. Understanding of the mineralogy, chemistry, origin of the basic and ultramafic rocks throw light on the processes of the mantle.